If you want a perfect 70 out of 70 in theory of computation, you need to stop memorizing disconnected rules and start seeing the underlying architecture of these machines. This is your exact blueprint for the exam. Every automaton we study is a basic machine that gains computational intelligence by bolting on a progressively more complex memory system. We map this evolution using the 4-level Chomsky hierarchy. It starts at the center with simple regular languages, expands to context-free, grows to context-sensitive, and reaches the outer limit of recursively enumerable languages. Each of these language rings is locked to a specific hardware equivalent. Regular languages run on finite automata with zero memory. Context-free requires a push-down automaton with a stack. Context-sensitive needs a linear bounded automaton. And recursively enumerable demands the infinite tape of a full Turing machine. Recognizing a language's memory boundary gives you an instant advantage. The moment you identify the language type in an exam question, you automatically know the exact machine architecture you have to construct to solve it. Let's apply this to context-free grammars. When converting a CFG into Chomsky normal form, you must follow a strict 4-step order of operations. First, eliminate epsilon productions, then unit productions, then useless symbols, and finally restrict the rules. If you mix up this sequence, say by deleting useless symbols before clearing out the epsilon productions, you will break the derivation tree entirely. Epsilon productions can create new useless symbols when they resolve, so order is absolute. Take this exact 8-mark question from the May 2023 paper. We have the starting production S yields AABB. By applying our steps sequentially, we mathematically replace the variables until every rule produces exactly 2 variables or exactly 1 terminal. This forces the language's derivation tree to snap into perfectly straight binary branches, with every parent having exactly 2 children. This uniform 2-child node structure allows modern compilers and parsers to process source code with absolute mathematical predictability. Moving up the memory hierarchy, we reach pushdown automata. A PDA introduces a last-in, first-out stack. The operational rule here is simple. Push a marker to the stack for your first item and pop that marker when you read the matching item. For the November 2024 question asking for a to the power of n, b to the power of 2n, we adjust that rule. Because we have twice as many b's as a's, we push 2 a blocks onto the stack for every a we read. Then we pop 1 block for every b. A post machine handles memory differently. Instead of a stack, it uses a first-in, first-out queue. To solve the 0 to the n, 1 to the n problem from the May 2024 paper, we read elements from the front of the tape and push our tracking markers to the back, cycling through until the queue is empty. Before you draw either of these transition diagrams on your exam sheet, write out the formal 7-tuple mathematical definition. Skipping the tuple is the most common way students bleed easy points on these design questions. When you visualize the physical geometry of your memory space, knowing whether you drop blocks down a vertical stack or slide them through a horizontal queue, you eliminate logic errors during complex state transitions. That brings us to the Turing machine. This leaves simple string matching behind. It operates as a fully functioning random access CPU capable of active computation. Try active recall on the unary subtraction problem from the 2024 paper. The logic requires the head to scan left and right, matching a 1 on the left, replacing it with an X, then finding a 1 on the right, replacing it with a Y. You must also map the edge case where the first number is smaller, ensuring the machine outputs 0. Building the machine is only half the subject. The other half is knowing its theoretical limits. A problem is decidable if an algorithm exists that eventually halts and outputs a yes or no for every possible input. As the halting problem proves, some questions are simply outside the reach of any machine. But even when a problem is decidable, it may be practically unsolvable due to time. This is the realm of computational complexity. We divide solvable problems into classes like P, for those solvable in polynomial time, and NP, for those we can verify quickly. According to Cook's theorem, SAT is the center of the NP complete class, the hardest problems in NP that every other NP problem can be reduced to. Identifying these complexity classes is vital for any computer scientist. Recognizing the problem as NP complete tells you to stop searching for an impossible shortcut and start looking for efficient approximations working in the real world. The final architecture you need to know is the universal Turing machine. This is the theoretical ancestor of all modern software, a machine designed to take the encoded description of another machine as its input data. For the exam, you must draw its specific three-tape architecture. Tape 1 holds the simulated data, Tape 2 stores the encoded rule set of the machine being simulated, and Tape 3 tracks the current state. Before wrapping up, check your notes on the final exam trap: finite state machines with output. Memorize the distinction that more machine outputs depend entirely on the current state, while mealy machine outputs depend on both the current state and the current input. This matrix is your complete study guide. It unifies the language hierarchy with their required hardware, lists the specific pumping lemma constraints, and maps out the exact closure properties for union, intersection, and clean star across all levels. Take a screenshot of this matrix right now. Use it to run through your active recall exercises, map the boundaries of your memory structures, and claim your perfect score.